Okay, oops, where are we not? Okay, so we started talking about banking angle. And it sounds like we just drew the diagrams, right? Yep. We didn't derive the equations yet.
Nope.
Okay, so we've got a couple of cars. So when we are going around in a circle, we remember that if we have a flat surface, the thing that's pushing us towards the center of the circle, the thing that's causing the circular motion, is a force of friction that's the Earth is placing on the car. It's because of the way that our wheels are turned and the way that we're driving, the Earth pushes the car towards the center of the circle, and that makes it go in the center of the circle. But if the road is banked, then there's going to be some additional things that are going on. And the force required to keep the car on the circular path is still going to be the centripetal force, right? We're still going to call it the centripetal force. And we still can say that that's the same thing as mass times centripetal acceleration. We can still say that that's the same thing as mass times velocity squared over r, which is our centripetal acceleration formula, right? V squared over r. But there's going to be some difference in what the sum of the forces is, okay? And again, in this circumstance, it's just going to be the static friction of the road for the car. But in this case, there's going to be some differences. On the first diagram, and we already drew some vectors, didn't we?
Yeah.
Yeah.
Okay, so we're going to draw a vector for the centripetal force required to keep the car in circular motion. Okay, so we're just going to draw centripetal force vector. This is a force that other forces acting on the car, whatever they might be, need to provide without a banked curve. Remember, it was only this force of static friction that could provide this. Recognize that in the banked situation, it will not just be static friction keeping the car in circular motion, but also a component of the normal force. Okay, so whatever this centripetal force is, it could be made up of more than one thing. It could be made up of the fact that there is a normal force acting on it, and I've said draw a normal force vector on the second diagram.
Yeah.
We did draw that, right?
Yes.
So there's a normal force. And I think we started some discussion about it as well. Draw the x component of the normal force and write a formula for it. Okay, so there's an x component of this force. Okay, and we can say force normal x. But then I cautioned you that this is not the adjacent side of the normal force vector, so it's not going to be the normal force times the cosine of theta, right? Because we said that since the gravity vector is straight down, and normally we're going to say that this is our angle because this is going to be our perpendicular force, and that's going to be our parallel force. Actually, it should be more like that, right? So it's going to be more like that. Okay, this angle is theta, and if I go straight up, this is the angle that's going to be theta, not this angle here. So it's actually, right, because it's, if I've got alternate interior angles here on the side of two parallel lines, if I drew another parallel line there, I could show you that. But anyway, I've got these angles here, and this is also going to be the same as this angle. So this is going to be the opposite side. So the normal force in the x direction is actually going to be the normal force times the sine of theta. Okay? Although that theta is still the angle of elevation. I've got it. Okay, so whatever this normal force is here, the x component of the normal force is what's causing some of the centripetal force. Okay, so that's something that's a little tricky and difficult to understand. The other thing that we said was that if I have the correct angle here, this normal force can actually provide all of the centripetal force. I don't need to actually even use friction to help me be pushed towards the center of the circle. So I've said, in fact, for a given angle of banking, there will be one velocity at which the x component of the normal force will actually equal the centripetal force. So what we're going to do is we're going to say this force, the centripetal force equals mass times centripetal acceleration equals mass times v squared time over r equals the normal force times the sine of theta. Okay? So at the above described velocity, and that would be this velocity here, right? Recognize that the s component of the normal force is providing the exact amount of force necessary to keep the car in a circular path with no help from static friction. And road banking is often designed so that this will be the condition for a particular speed, and this will be called the design speed. Okay, so there will be a speed where the engineers feel like this is the safest speed that we can have going around this curve, and we're going to design the banking in the road to match whatever that speed is. So in the above formula, in order for me to make this work, I need to know how to find the normal force. Okay? I need to know how to find the normal force. And my practice has been, in order to find something like this, I can't find this based on my force due to gravity here. I'm going to need to find this in a different way because of the way this is set up. And what I want to do is define the normal force in terms of something else that's going to be useful. And so I recognize I have another side here. This is the y component, right? This is going to be the normal force, the y component. And that's also going to equal the normal force times the cosine of theta. And we've had some experience with this now. Would it be possible for me to define this in terms of, define normal force in terms of these other two things? Could I say that the normal force is the force normal in the y direction minus or divided by the cosine of theta? And oh, by the way, what does this also have to equal?
mg.
Has to equal mg, right? Because I've got mg down there. So could I not say that mg equals the normal force times the cosine of theta? Then I could say the normal force equals mg divided by the cosine of theta. And just like magic, this kind of seems to fall into place here. Now what if I substituted mg over the cosine of theta for the normal force in that? I could say mg over cosine of theta times the sine of theta. And I know that the sine of theta over the cosine of theta is the tangent of theta. So my Fnx now equals mg times the tangent of theta. Wow. I can go back down here then, and I could say mv squared over r equals mg times the tangent of theta. And it doesn't matter what the mass of my car is anymore, because the masses cancel out. And I can then find out that if I multiply both sides of the equation times r, that v, that velocity at which this works, where I have an angle that is going to just use the normal force to keep my car going in a circle, that velocity is going to equal the square root of rg times the tangent of theta. Okay? So I've said in the above formula, how would we find normal force in order to solve for the x component? In this case, recognize that the y component of the normal force must equal the opposite of mg. This allows you to create an alternative expression for normal force, which you can substitute the original equation. And so I could also have this particular formula here. What I set up here was v equals the square root of rg times the tangent of theta. But I could also have said v squared over rg equals the tangent of theta, right? Okay, so that could have been another way. And then how would I have found the angle at which this works?
The inverse tangent.
I take the inverse tangent times v squared over
RG.
or divided by rg. Okay? So we've got that here. This is called the banking angle, and this formula is called the design speed. Okay? We could also find the radius for the curve of the given angle and the velocity. If I knew what the angle was, I could also figure out what that radius is, and this radius is going to be called the radius of curvature. Okay? So here's the problem with all of this. You will not be given any of this. Well, you'll be given this on the test, but you won't be given any of the other stuff on the test. So in order to find out what the design speed is and the banking angle is, you're going to have to know how to get from this expression for the centripetal force, right? This is the centripetal force. That's the x component of the normal force, right? F normal times the sine of theta. You're going to have to know how to get from here to here. And I'm not sure why I still have the negative signs in there. The negative sign is there, but we also know that the acceleration due to gravity is negative, so that cancels those things out. Okay? So that should just be mg tangent of theta. So we have a couple of new formulas. We have that theta equals, 16, I forgot that already. The inverse tangent of v squared over rg. And we have that v equals the square root of rg times the tangent of theta. Okay, and this all comes from understanding that the x component of the normal force is what gives rise to the centripetal force, right? That's all I'm doing. I'm saying, and hopefully you figured out by now, situation after situation after situation, we've said something is causing this particular force, whether it's the tension, whether it's gravity, whether it's something else. We've always equated this thing to some other force. And that's the process that we go through to figure these things out. So for a car traveling with speed v around a curve of radius r, determine a formula for the angle at which the road should be banked so that no friction is required. Okay? What is the angle for a road which has a curve? Oh, for a car traveling with speed v around a curve of radius r, determine a formula for the angle. We've already done that, right? We've got that. So that is this, determine an angle. What is the angle for a road which has a curve of a radius of 50 meters with a design speed of 50 kilometers per hour? And so I should divide this by 3.6 immediately to get, if somebody can do that, a number of meters per second. So we're going to say theta equals the inverse tangent of whatever that velocity is squared. And that's always going to have to be in meters per second.
Yeah, 55 by 3.6 is 13.8 continuing.
13.8, you said?
I said 8 continuing, so 9.
Oh, 8 repeating, so 13.9 meters per second. That's going to be squared divided by 50 meters times 9.8 meters per second squared. Okay? And in this circumstance, I'm just going to leave the negatives out because if we did this correctly, we would have had a negative there and it would have canceled out the negative for 9.8. So somebody calculate the inverse tangent of this for me. I don't remember what that turned out to be. What did you get?
Not bad. So inverse tangent of 13.9 squared, which we did, and divided by 50 times 9.8.
Okay, so I squared 8.9 and divided that by 50 times 9.8, and that gave me 0.39, and then I took the inverse tangent of that. I have to do it backwards on this calculator rather than. So did you get the same? Did you get 21?
Yeah.
Okay. Why didn't you get 21.5? Okay, you have to really make sure you put the numbers in right here and use all your parentheses. Obviously, if I had one of your calculators, I would get second tangent and then it would give me parentheses, and I would probably have a second
It's
set
because
of
I'm in
parentheses.
radians.
Huh? Oh, you're in radians?
Yeah.
Okay. So it equals 21.5 degrees. Okay, that's a pretty steeply banked road.
Yeah.
Okay. So this sort of makes sense?
Yeah.
Okay. So let's draw two more of the same thing. And we're going to recognize that if the car is traveling slower than the design speed, okay, if the car is traveling slower than the design speed, it should make sense that my x component here, F normal times the sine of theta, is actually going to provide more force than it's necessary, because this x component here isn't going to change. If I slow down, the x component of the normal force is going to stay the same, but the decreased velocity is going to be that I'm not going to need all of that force. Okay, so what I'm saying here is that recognize that if the car is traveling slower than the design speed, the x component of the normal force will actually be providing greater force than necessary to keep the car in circular motion. What does this mean for the force of static friction? What is the force of static friction going to be doing in this case?
It's going to decrease.
Okay, so I'm going to actually have more force here than is necessary. Okay, I'm going to have more force than is necessary here. And the static friction, what direction is the force of static friction going to be going in that case? If I've got enough force or more than enough force here, what's the force of static friction going to be doing? What direction is it applied in?
Opposite?
It's going to be applied up the curve, isn't it?
Yeah.
Okay? It's going to be applied up the curve. Okay? And I'm going to have a component of that balances this, because obviously I'm not accelerating. Well, actually, it's not going to balance that, is it? Because I still need to accelerate towards this direction, right? So the component of this, there's a component of this force up the curve here that is going to balance, or it's going to oppose this. And I'm going to need to have this going up the curve, and that's going to prevent my car from sliding down the curve, right?
Yeah.
Okay, but at some point, I'm going to probably worry about the car's going to actually start sliding down the hill, because that force of friction isn't going to be able to work. What does that mean for the force of static friction? The force of static friction will be directed up the curve and will keep the car from sliding down. But I can ask the opposite question. If the car is traveling faster than the design speed, the x component of the normal force will actually be providing less force than necessary to keep the car in circular motion. What does that mean for the force of static friction then?
It will be going down.
The force of static friction is going to have to be applied down the curve because I'm going to need a component of that plus the component of the normal force to keep it going in a circle. Okay? So if I'm going slower than the design speed, the force of friction will be applied up the curve, and that will keep my car from sliding down the hill. If my car is going faster then directed down the curve, and we'll keep the car in circular motion. And part of that will also keep the car from sliding off the curve too, right? At some point though, if I'm going too fast, then the combination of the bank and the static friction is not going to be able to keep my car traveling in a circle, and I'll start to slide, and then I'll just keep going straight, right? I'll go over the top of the bank. Okay, and that's more of a conceptual thing. They would never ask you to analyze the forces in this situation. That's just too complex. But they might ask you a conceptual type of question about that, like what direction will the force be, the friction force be applied in one of those circumstances, which is why I brought it up. Okay. Now, it should be intuitive that a constant force constantly directed perpendicular to a path will provide uniform circular motion. If I have a constant acceleration directed towards the center of a circle, instead of my object going straight like it wants to, if that force is constantly directed perpendicularly to the direction of motion, right? I'm going to continue to travel in a circle. But what if the force is directed at some other angle to the path of motion rather than being exactly perpendicular? So for example, what if I have an object that's wanting to travel in a straight line, but I have a force that's directed in this direction instead of straight down, or let's actually draw it from the object. What if I have a force that's directed in this direction instead of a force that's directed towards the center of the circle? Okay? This may be the circumstance when you begin to accelerate a weight in circular motion at the end of the string. So if I'm doing one of these hammer things, or even swinging the thing around my head, okay, initially when I start that motion, I'm not going to be at exactly the center of the circle, am I? I'm going to be a little off center as I start that motion, and I'm going to actually have a circular motion like that myself, whereas if once I get it going and it's constantly in constant uniform motion, then I'll be pretty much at the center of the circle, right? So I'm going to be a little off center as I start that. Okay, so this may be the circumstances you begin to accelerate a weight in circular motion at the end of a string, or a hammer throwing, the thrower beginning to accelerate the hammer. If you think about it, the point from which you are accelerating, stop that. The object in circular motion is not the exact center of the circle, it's slightly off center. This would make the direction of force at an angle to the circular path. Okay, so my force is not going to be directed towards the center, it's going to be slightly off center. It's not going to be, the path of the force is not going to be perpendicular, it's going to be not directed towards the center of the circle. And under those circumstances, I will also change the speed around the circle. Okay, so not only will so if my force is directed there, not only will I cause my thing to go in somewhat of a circular motion, and it won't be entirely circular initially, but I'm also going to cause an acceleration around the circle. Okay, I'm going to cause an acceleration around the circle. Okay, so I'll actually change the speed around the circle as well. I won't be in uniform circular motion. So to understand this issue of when an object is undergoing both centripetal acceleration and acceleration along the path of motion, okay, we have to split the force that is at an angle to the path of motion into two components. Okay, one of these is going to be, so if my motion is sort of circular to begin with, but my force is directed at an angle trying to get it started, right? I'm going to start from an initial velocity of 0 and try to get it going faster and faster until I get to a uniform circular motion, okay? I'm going to have a component of that is directed towards the center of the circle, and I'm going to have a component that's directed away from the center of the circle, okay? This is still going to be the centripetal force, and I'm going to have one that's tangential to the direction of motion. I'm going to have a force that is directed like this, okay? So I'm going to have a force directed towards the center, and I'm going to have a force that's directed tangential. And what I mean by that is that that force is touching the circle at one point. That's why we call it the tangential force. So I'm going to have a centripetal force and a tangential force. The tangential force is going to cause my motion to accelerate along the path. My centripetal force is still going to cause acceleration towards the center of the circle. And I've said draw this idea. That's what I just did there. So you don't have to draw it if you don't want to. But that's what's happening here. And the sum, or my overall acceleration, my centripetal acceleration plus this tangential acceleration, is going to be the acceleration. Okay? So I'm going to have force C and force tan added together, and then this force here would be just the overall force. It would be the sum of Fc plus F10, and it would just be the force, and that would cause the overall acceleration. So I've drawn that idea. Okay, so the centripetal component of the acceleration arises because of the centripetal component of the force is still going to be v squared over r. That acceleration, that AC, or that centripetal acceleration, is going to be v squared over r. The direction of this is still towards the center of the circle. Because the speed of the object along its path of motion is also going to change, the formula for acceleration caused by any tangential force is the standard acceleration along a path. It's going to be the change in velocity over change in time. And the direction of this will always be parallel to the velocity vector. Okay, so I've got my centripetal force in that direction, and I've got my tangential force in this direction. Okay, the acceleration related to this is going to still be v squared over r. The acceleration related to this, however, is going to be the change in velocity over the change in time. But if the object is speeding up, it will be in the same direction. If it's slowing down, it will be in the opposite direction. So I could be slowing down too, right? But whatever the acceleration related to this tangential force is, it will be parallel to the velocity, right? My velocity, I want to be going straight, right? I don't really want to be going in this commercial circle. So at any point here, the velocity vector is going to be perpendicular to the centripetal force vector or the centripetal acceleration vector. And the acceleration tangentially is also going to be directed that way. Okay? So the forces and accelerations are always perpendicular to each other. The total acceleration is the sum of the two acceleration vectors. And because these are perpendicular, the magnitude is always going to equal the square root of the sum of the squares. So whatever this acceleration is, okay, and I can draw that again here. Whatever that acceleration is, I've got acceleration towards the center of the circle, AC, which is v squared over r, and I've got tangential acceleration, which is delta v over delta t. Okay, the sum of that, and what I can do is I can move that down here, right, so I can see what the resultant is. The vector sum of that is just going to be found by the Pythagorean theorem of both of these, right? So A tan. If I need to, I probably won't have a problem like that on the test, or the AP won't usually have a problem like this on the test, but just in case, they might ask you to find the actual acceleration if you know what the tangential acceleration is and what the centripetal acceleration is. Okay, so an example of this would be a car, a race car traveling around a circular track. Okay, it's going to start at a zero velocity, right? And it's going to speed up. So it's going to have a tangential acceleration that causes it to speed up around the track. It's going to start at zero and it's going to do this, right? It's going to speed up until it gets to its constant velocity. So I've got an acceleration, a tangential acceleration that's causing it to accelerate along its path, and that's always going to be directed perpendicular to the radius. And then I've got an acceleration that's always directed towards the center of the circle as I'm going in that circular motion. So a race car starts from rest in the pit area and accelerates at a uniform rate to a speed of 35 meters per second in 11 seconds, moving on a circular track, a radius of 500 meters. Okay, so I don't need to know anything else about the motion to find the tangential acceleration. I know that if I want to find the acceleration, I've got a final velocity and I've got an initial velocity of v0 and I've got a time. So I know that I can use v equals v0 plus acceleration times time to find that acceleration, this acceleration that's going around the outside. And so that drops out, and that acceleration equals v divided by t equals 35 meters per second divided by 11 seconds. If somebody can divide that for me. $3.9?
Yeah, 3.18.
Okay, okay, so 3.18 meters per second squared. Okay, and my velocity is changing, but my acceleration around the circle is the same all the way around, right? It's a constant acceleration around that circle of 3.18 meters per second. So but no matter where I'm at on this circle, at that point in time, that acceleration, which is perpendicular to the radius, that acceleration is 3.18 meters per second squared. Okay, so I've got a tangential acceleration of 3.18 meters per second squared. Okay, then it says find the radial acceleration at the instant when the speed is 15 meters per second. Well, I also know what the centripetal acceleration is, right? AC or AR equals V squared over R. And so at that instant, when it's 15 meters per second, 15 meters per second squared divided by the radius of 500 meters, and you can find that acceleration for me as well.
0.45.
0.45 meters per second squared. Okay, so if I start at 0 and I get to 15, I don't know, maybe that'll happen somewhere like right there. So at that instant, I'm going to have that tangential acceleration, and I'm going to have that tiny little centripetal acceleration. Okay, so if I say that I have a tangential acceleration of, oops, let's make that vector a little longer. And then I have a centripetal acceleration of 0.45 meters per second squared. If I put this vector down here so that I can see what the result is, that acceleration, that overall acceleration is going to be directed like that, isn't it? So there, there. And I can find out what the overall acceleration in this direction is going to be by finding the Pythagorean theorem of 3.18 squared plus 0.45 squared. So if you could figure that out for me as well.
$5.51.
5.51 meters per second squared. So the overall acceleration at that point would be 5.51. I haven't gotten to a high enough speed where I need a lot of force to keep me going in a circle yet. So I won't really get until I get to a much higher velocity, I won't really get to a point where I've got to have a lot of centripetal force to keep me going in a circle. Right now, most of my force is going towards accelerating me along the path, whereas only a small amount of my acceleration or my force is going towards keeping me in a circle. When I get to a much greater velocity, though, I'm not going to require as much velocity to speed me up further. I'm going to require more of that force or that acceleration to keep me going in a circle. So those are, it's mostly conceptual, but be prepared for the possibility of having to figure out what the overall acceleration is in that circumstance and recognize how you would do that. But it's not something that's likely to happen on the AP test. Okay, so the big thing that this applies to mostly in our lives is keeping us on the surface of the earth, okay? The point where we need to really, really understand this and just recognize how much of a genius Newton must have been. He was the one that came up not only with his 3 laws of motion, but he also came up with the law of universal gravitation. And it makes a lot of sense to us now because we've had 300 years of people explaining it to us. But, I mean, he was the one that originally came up with this in a way that makes sense. And to understand that this is probably a universal law everywhere in our known universe, this law acts the same way. Gravity doesn't act any differently anywhere else than it does here. And we know that because we've looked great distances and we understand the motion of galaxies related to each other, and those observations have allowed us to say, you know, this must actually be true. Now, is there some other universe, alternate universe, where gravity works in a different way? I don't know. I don't think so, but I can't say no for sure. But anyway, Newton concluded that the same force that attracts and accelerates objects towards the surface of the Earth must be the same force that attracts the moon and holds it in its orbit. Why would a force such as gravity be controversial at Newton's time?
People didn't believe it
But why?
because it seems improbable.
Why?
An invisible force is.
Okay, that's the key word. It's invisible. I can't see it, right? I can't see the force due to gravity. If I push this, I can see my finger pushing that object, right? But I can't see that force that is pulling things towards the center of the Earth, okay? Because I can't see it, it's going to be controversial. It doesn't really have anything to do with the fact that some religious people might object to it. It just doesn't make sense that I have that. Newton further concluded that this force of attraction depended inversely on the square of the distance between objects. And here's how he reasoned this. Okay? So, if we know that this acceleration towards the center of the Earth is in fact true, and that it has this relationship between velocity and the radius, they knew how far the Earth was from the center of the Earth at that time. I also know that the circumference times the radius, or 4 pi squared r, is going to equal this value. And I know that there are this many seconds in the month. Okay, so if I multiply 60 times 24 times 28 days, or 28 and a quarter days, however long it takes the Earth to go, or the moon to go around the Earth, I get this many seconds. I end up with a centripetal acceleration of 0.00272 meters per second. Okay, so if I apply the same features to the moon's acceleration towards the center of the Earth that I apply to things here on Earth, I come up with the fact that the moon is being accelerated towards the center of the Earth at a very, very tiny rate, 0.272 meters per second. But again, it's still this same idea that if this is the center of the Earth and this is the moon wants to be here at this time, but the Earth has pulled it into a place where it's accelerated towards the center of the Earth here, okay? Moon wants to be here, but the Earth says, no, you're going to be here at this point. I've pulled you from this point to this point. I've accelerated you towards the Earth by this amount during however much time it took you to get there. Okay? Okay, so if, let's see. Okay, so if I divided this by the acceleration due to gravity at the surface of the Earth, okay, so if this is the acceleration of gravity as far as the moon is concerned, but at the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared. This is 1/3600th times this value. Okay, this is 1/3600th of this value. So the acceleration due to gravity on the moon is 1/3600th of the acceleration of an object at the surface of the Earth. The moon is 348,000 kilometers from the center of the Earth. The surface of the Earth is about 6,380 kilometers from the center. Okay, so this is about 60 times this. So the moon is 60 times farther from the gravitational center of the Earth than is the surface of the Earth, and the force due to gravity is 1/3600th. Okay, so the force due to gravity must be related to the square of the distance. 3600 is 60 squared. Okay, so what we're saying here is that the moon is 60 times farther from the gravitational center than the center of the Earth. Okay, so here's the Earth, here's the center of the Earth, and the moon is 60 times farther away. Why can't I write there? Okay, let's say that this is 60 times what this is. Okay, the moon is 60 times farther away, but its gravity is 1/3600th of that. So the force due to gravity must be related to the square of the distance. Okay, so if I'm 60 times farther away, my force due to gravity, if this is true, would have to be 1/3600th of what it is at the surface of the Earth. Okay, so he had the brilliance to figure this out. Okay, and even after walking through it, it's still a little bit nebulous, but the force due to gravity is going to be related to the square of the distance between things. Further, and you don't need to know that derivation, you just need to know the result of that. You need to know that the force due to gravity, F big G, is proportional to the square of the distances, or the inverse of the square of the distances. Okay? So, Newton further concluded the gravitational force of attraction was proportional to the masses of both attracted bodies. And that makes sense to us, doesn't it? The heavier, the larger the object, the more massive the object, the more gravity is going to be, the more gravitational force. Experiments on Earth showed that the force due to acceleration, the force due to the acceleration due to gravity increased with mass. Newton also knew that if the Earth exerted a force on the moon has to exert an equal and opposite force on the Earth. Okay? And that, again, is something that's hard for us to believe because the Earth is so much bigger. And for me to say, well, the force that the moon is attracting, the Earth is attracting the moon with, is the same as the force that the moon is attracting the Earth with, seems ridiculous until you think about what would be happening. The moon would be accelerating towards the Earth if that wasn't the case, right? But also, what we end up thinking is then that the force, whatever this force happens to be, is going to have a much greater effect on the moon than it is on the Earth. And that's how we kind of resolve that contradiction here. It seems like the force that the Earth would be pulling on the moon with would be much greater than the force that the moon is pulling the Earth with, but that's not the case. They're equal according to Newton's third law, but whatever that force is going to act more strongly, or it's going to have more effect on this because the mass of this is so much smaller. But because of this symmetry, Newton reasoned that the gravitational force of attraction between two bodies must be proportional to both masses. Okay, so the force is going to be proportional to the product of the masses. Okay, so the force due to gravity is going to be directly proportional to the mass of the Earth and the mass of whatever object. So if this is the moon, if I increase the mass of the moon, you would expect the force of gravity to increase as well. If I increase the mass of the Earth, you would expect the force of gravity to increase as well. If I increase the distance, if I double the distance, you're going to expect the force due to gravity to decrease by 1/4. It further concluded that as the sun and planets appear to behave in the same fashion as the Earth and the Moon, they also must be under the same force influence of the same forces. So he considered this to be a universal force. So as far as we know, every particle in the universe attracts every other particle with a force that's proportional to the product of their masses and inversely proportional to the square of the distances between them. This force acts along the line joining the two particles. This is called an inverse square law. Okay? There are other laws of force that act in a similar fashion. For example, the force of attraction or repulsion between charged particles, the electrical force, equals a constant times the charge of one force times the charge of the second force divided by the square of the distance between them. Okay, if I double the distance between charged particles, I decrease the force by 1/4. If I double one of the charges, I double the force of the force, or I double the force. If I quadruple one of the charges, I quadruple the force. But if I double the distance, I quadruple, or I decrease the force by 1/4. Okay? So this is an inverse square law, and there's a constant here that makes this work. I don't need you to know the units of this constant. You'll be given this anyway on the test. They'll give you this constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay? Be aware that if the gravitational bodies are large and irregular, to find the total gravitational force, the bodies must be considered as a collection of particles, and individual forces of gravity must be connected between individual particles and summed, and this requires calculus. So if I have an exceedingly large body here, and I've got a different density in this part than I do in this part, than I do in this part, I have to consider the gravity as the sum of all of the gravities of all the infinite numbers of masses here. Okay? If I have an irregular density, I would have to consider the gravity of this as the sum of all of the gravities of the individual particles that make this up. Okay? We don't get that complicated. That requires calculus. We don't get that complicated. Thank God.
Are you going to get that kind of calculus this year?
Huh?
Are we going to get that kind of calculus this year, you think?
No.
No? That's what I thought.
No, in your calculus class, you mean?
Yeah.
No.
That sounds kind of dumb.
Yeah.
No, that's beyond, that would be something that we might attempt in the advanced topics to math class if we were to be able to have that. Okay, again, a plug for that. 50 kilogram person and 70 kilogram person are sitting on a bench close to each other. Estimate the magnitude of the force of gravity that each exerts on each other. Force due to gravity. All I need to do is apply this formula. Force due to gravity, I need a formula, G times mass 1 times mass 2 divided by the square of the distance between them. R squared equals 6.67 times 10 to the negative 11th. And I'm not going to make you write the units out for that. And we're going to say 50 kilograms times 70 kilograms divided by, and if you're sitting on a bench, let's say you're 1 meter apart. So 1 meter squared. Okay, so multiply 6.67 times 10 to the negative 11th times 50 times 70. should be in the range of 10 to the 9th, I would guess, or 10 to the 8th, maybe. Negative 8th, I mean. What do you get?
I got 2.3345 times 10 to the negative 7.
Okay, that's close enough. So 2 point what?
2.3345.
433 times 10 to the negative
7.
7 newtons. Okay, that's kind of a tiny force, right? I don't have any device that can measure that small of a force. But you and I are exerting forces of attraction, gravitational forces of attraction on each other. They're just so small that it's not going to affect any of us, right? We're gonna hang where we are. But get used to the idea, 10 to the negative 11th, oh, I see what I did here. So 50 times 70 is 3,500. Okay, so that's 10 to the third. So if I'm going to multiply 10 to the negative 11th times 10 to the third, I'm going to be somewhere in the range of 10 to the negative 8th, right? Because I'm going to add these two numbers together. Negative 11 plus 3 is negative 8. So this answer is close enough to me to make good sense. So if you're within 1 unit in your exponents when you do that kind of a thing, you've probably gotten the right answer. Now, if you'd ended up with 10 to the negative 14th, then you would have realized, hey, I must have done something wrong in my multiplication. Okay? So let's stop there and we'll continue with gravitation. We're going to come upon a relationship in the next couple of lectures that's going to really just blow your mind. A universal relationship that's just going to blow your mind.